All right, back at it. So what do we have here? Previous video, we talked about the following theorem. T from V to W, assuming this dimensionality constraint, and we get this really beautiful result, in which case it's enough to show that T is injective, or that T is surjective, not the and there, to show that T is invertible. So this actually proves to be very useful, and I wanted to illustrate that with one example from my boy Axler's Linear Algebra Done Right textbook. And so it kind of goes like this problem. It gives you this crazy looking expression where you're taking the second derivative of this, x squared plus 5x plus 7 times p. And we're trying to show that given any random polynomial, all right, remember p of r is just all the polynomials with real coefficients, okay? Given any such polynomial, okay, we're claiming that you can actually find a p so that this holds, right? Now how the heck, without all of our knowledge here, would we prove this? Well, I don't know, but we also don't know as of late how to prove it with this knowledge here, so that's kind of a Dumbo question to ask. But again, this looks really complicated. Like, I don't really know how I would approach it at first, but given that this appears right after this theorem here, we have a little bit of a hint. And so how could we reframe it a little bit in terms of this language of surjectivity and injectivity? Well, we're trying to find, I've kind of said it in words, haven't I? Given anything in the set P of R, all the polynomials with real coefficients, we're trying to show that some kind of function that we're applying to P, right, outputs, there exists some input for this function, wacky looking function here, that gives Q, that gives that random choice of a polynomial. Okay, so now we have something to work with. That sounds a lot like surjectivity, but we have to define what kind of function we're working on first, right? Well, it's right here, it's laid out for us. So T from, well, we're taking P in polynomials, right? So P with real coefficients to the same thing, right? So it is indeed an operator. We're acting from one set to another. So clearly their dimension, does it equal one another? Because the dimension of all polynomials, well, you could have polynomials with degree 1, degree 2, degree 5, degree 667. So what do? That could go on infinitely. This is infinitely dimensional. So the dimension, it's not finite, it's infinite. Does infinity equal infinity? All right, I don't know where we're going with that. Our previous result doesn't really help for that because we can't quantify whether these two dimensions are equal. Infinity equaling infinity, that's kind of a dubious thing, right? Okay, so what do? First of all, let's define what we want that function to be. We're getting ahead of ourselves. So we're mapping, T is defined by mapping some polynomial there to, let's say, well, it's here, right? So x squared plus 5x plus 7 p, take the second derivative of all of that. Okay, that's our function. All right, again, this is linear because the derivative is linear, so we don't have to worry too much about that. That's very nice. Okay, but again, coming back to that problem, we want to show this is surjective, okay? So we're using that theorem. If this was finite dimensional, assume that for a second. If we showed it's injective, which might be easier to do, and we'll see it's easier to do, then we could basically imply that it's surjective. But we can't do that here. The magic doesn't apply here, in Axler's words. The magic doesn't work here because these are infinitely dimensional, okay? But how do we get around that? Well, if you think about it, right? Given any input, okay? Let's say our Q, the Q that you're looking for in our problem, all right? Let's say it has some degree, right? Any given polynomial, it doesn't have infinite degree, right? It has to have some degree, let's call it, so I'm gonna say the degree of Q is like M, for example, okay? And that's some non-negative number, right? Let's say it's a natural number. It's a debatable term. Some people say the natural number includes 0, others don't. I digress. I will not partake in that debate. Basically, do whatever you want. It's a free country, okay? So the degree of this is equal to M. So then, I mean, what is this T map Q to? Okay. Well, I should say, if degree of Q, so we're looking for P, sorry, I kind of misspoke there. If we're looking for P so that x squared plus 5x plus 7 times P, second derivative of that is equal to Q, what does the degree of P have to be for this to make sense? Well, okay, we're augmenting the degree of that by 2 here by multiplying P by something with degree 2, so those degrees obviously add up, right? Because your max degree multiplies your max degree of P, exponents add, so it'll add up. So P, and then we differentiate it, so twice, right? When you differentiate, if you remember from your calculus class, your exponent goes down by 1, and so we've done it twice, so it goes down by 2, so it cancels the effect of this multiplication. So really our degree never really changes between P and Q. Okay, so that means really we're taking inputs for P in the polynomials with max degree n, and we're also taking outputs in the polynomials of max degree n. Okay, this is good because that's something we can work with. If we instead put that n there, okay, so instead of looking at infinitely dimensional thing, we can now work with this finitely many dimensional thing. If you've seen this in notation, I shouldn't have just thrown it at you guys kind of raw like that. But that m subscript means polynomials of order less than or equal to m. Okay, this is finite dimensional, and you can show that a basis of that is 1x, x squared, dot, 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 x to the m. It's really not too hard, because if you look at linear combinations of this, all right, those are exactly just polynomials, like a0 plus a1x plus dot, dot, dot. That's just the form of a polynomial, so it's actually very clear. So indeed, it's finite dimensional. Great. Okay, now we're in business. Okay, so let's find the null space of this, because if we again use that injectivity, we can show surjectivity, and then we can prove this result. We can know for a fact that there is such a P that satisfies this. Okay, just by what we've just mentioned. Right? Because Q is taken in this output space, which happens to be the same as this input space. Thus, their dimensions are the same, okay? But then we want to show that when we apply T to this P, to some P, that it equals Q. So again, this is the same as being surjective. Any output is mapped to by some kind of input in the input space. That's exactly what we want to show. And to show surjectivity, we show injectivity. Showing injectivity, we show that the null space is trivial. It's just 0. Okay, so let's find the null space of T. So what does that mean? That means all P, so that T of P is equal to 0. Okay, well, what does that mean? That means that we just plug in P here. Maybe it's not good to use P, but you guys know what I mean. So that means x squared plus 5x plus 7 is P, second derivative of that is equal to 0. Okay, well, what's going on here? We're taking the second derivative. Again, this expression has to be at least degree 2 because we're multiplying a polynomial. Now, the polynomial could definitely be constant. If it's constant, worst case scenario, that's the lowest degree it can be. It's degree 0. Then it is indeed degree 2 because you just multiply that constant through this polynomial. But if you take the second derivative of a polynomial, well, how far down does that increment go? You get, in this case, for example, 2x and then 2. We don't get 0. The only case we really get 0 is well, what happens if you look at things like ax plus b, right? If you differentiate that twice, you get, well, once is a, then it's 0. You can only have functions like this that you differentiate twice to get 0. You're never going to get functions like that here, okay? Because it's always going to be at least degree 2, assuming p is non-zero. If p 0, all of this goes to crap, right? It goes to shift, okay? So p has to be 0, and if it's not 0, this doesn't make any sense. There's no such solutions for x. And so this implies P is just equal to 0, and this implies the null space, I'll write it out here, is just equal to the 0 vector. And this implies injectivity, T is injective, which thus implies by this theorem here that that T is surjective. And that, ladies and gentlemen, implies exactly what we want to show here by what I've reasoned previously. Again, if you guys have any comments, questions, queries, means the same thing, but it sounds cooler. Enlightened advice, video suggestions, drop them down in the comments below. Like the video, subscribe. Sorry, I'm not gonna make you do all these things again. It's a free country, depending on where you are, so do what you want. If you did enjoy the video though, I would greatly appreciate you expressing that appreciation in the form of comments. It doesn't have to be these monetary numbers like counts or subscriber counts, but just a nice word down in the comments would be greatly appreciated. And on that note, the theoretical nerd out.